Hey there, future doctors and scientists. Physical chemistry might sound intimidating, but trust me, it's just a fancy way of saying the physics of chemistry. This stuff is the backbone of chemistry, explaining how and why chemical reactions happen. Now you might be wondering, Bill, why should I care? Well, my friends, mastering physical chemistry is like having the cheat codes for the NEET exam. Think of it this way: physical chemistry is the logic behind the magic of chemistry. It's like understanding how a bike works instead of just riding it. So, buckle up, because we're about to embark on an exciting journey through the fascinating world of physical chemistry, and I promise by the end of this guide you'll be saying, physical chemistry? Piece of cake. Let's start with the basics: atoms. These tiny particles are the building blocks of everything around us, from the air we breathe to the water we drink. Think of atoms like Lego bricks. Just like you can combine different Lego bricks to build amazing structures, atoms combine to form molecules, which make up everything we see and touch. Now, each element on the periodic table is defined by its atomic number, which is like its fingerprint. It tells you how many protons, positively charged particles, an atom has. For example, hydrogen, the simplest element, has an atomic number of 1, meaning it has 1 proton. The periodic table is organized based on the properties of elements. It's like a giant map that helps us predict how elements will behave and interact with each other. Understanding the basics of atomic structure and the periodic table is crucial for tackling more complex topics in physical chemistry. It's like learning your ABCs before you can write a novel. We all know about solids, liquids, and gases, right? But have you ever wondered what makes them different at the molecular level? That's where the kinetic theory of matter comes in. Imagine a bunch of tiny bouncy balls. Those are your molecules. In a solid, they're tightly packed and vibrating in place like a crowded dance floor. In a liquid, they have more freedom to move around like people mingling at a party. And in a gas, they're bouncing off the walls like kids on a sugar rush. Now, real gases don't always follow the ideal behavior we learn about in textbooks. Sometimes they get a little too close for comfort and start interacting with each other, which can affect their pressure and volume. Understanding the behavior of gases is essential for many topics in physical chemistry, so make sure you've got a good grasp on this bouncy, gassy world. Thermodynamics is all about energy and how it changes during chemical reactions. It's like the accounting system of the universe, keeping track of where energy goes and how it's transformed. One of the most fundamental laws of thermodynamics is that energy cannot be created or destroyed, only transferred or transformed. It's like the ultimate cosmic piggy bank. You can't make more energy, you can only move it around. Another important concept is entropy, which is a measure of disorder or randomness. Think of a messy room? That's high entropy. A clean room, on the other hand, is low entropy. In general, the universe likes to move towards a state of higher entropy. Thermodynamics can help us predict whether a reaction will occur spontaneously or not, and it's a crucial topic for understanding chemical kinetics and equilibrium. Section 5: Chemical Reactions, Finding a Balance. Not all chemical reactions go to completion. Sometimes they reach a state of balance called equilibrium, where the rates of the forward and reverse reactions are equal. It's like a seesaw that's perfectly balanced. The law of mass action describes this equilibrium state mathematically. It tells us that the ratio of products to reactants at equilibrium is constant, and this constant is called the equilibrium constant. Understanding chemical equilibrium is essential for predicting the direction of a reaction and calculating the concentrations of reactants and products at equilibrium. It's like having a crystal ball that lets you see into the future of a chemical reaction. Section 6: Electrons on the Move, Redox Reactions, and Electrochemistry. Redox reactions, short for reduction-oxidation reactions, are all about the transfer of electrons. One species loses electrons, which is called oxidation, while another gains electrons, known as reduction. It's like a game of hot potato, but with electrons instead of potatoes. Electrochemistry is the study of these electron transfer reactions and their relationship to electrical energy. Batteries, for example, are powered by redox reactions. Balancing redox reactions can seem tricky, but it's like solving a puzzle. Once you understand the rules, it becomes second nature. Electrochemistry is a fascinating field with numerous applications in our daily lives, from powering our smartphones to developing new energy storage devices. Section 7: Speeding up reactions, the world of chemical kinetics. Have you ever wondered why some reactions happen in a flash while others take ages? That's where chemical kinetics comes in. It's the study of reaction rates, or how fast or slow a reaction proceeds. Several factors can affect reaction rates, including temperature, concentration, surface area, and the presence of a catalyst. Think of a catalyst like a matchmaker. It helps bring reactants together in the right orientation to react, speeding up the reaction without being consumed itself. Understanding chemical kinetics is crucial for designing and optimizing chemical reactions, whether you're developing new drugs, synthesizing new materials, or simply trying to make your favorite recipe faster. Section 8. Surface chemistry. Interactions at the boundary. Surface chemistry is all about what happens at the interface between two phases, like a solid and a liquid or a liquid and a gas. It's like the cool kids' table of chemistry, where all the interesting interactions happen. Adsorption, for example, is when molecules from a gas or liquid stick to the surface of a solid. This process is used in many applications, from gas masks to water purification systems. Colloids are another important topic in surface chemistry. They're mixtures where tiny particles of one substance are dispersed throughout another substance. Milk, for example, is a colloid of fat droplets dispersed in water. Surface chemistry plays a crucial role in many biological processes, such as enzyme catalysis and cell signaling, and it's a rapidly growing field with exciting applications in nanotechnology and materials science. Section 9. Conclusion, your journey to NEAT mastery. Congratulations, you've made it to the end of our whirlwind tour of NEAT physical chemistry. Remember, mastering these concepts is not about memorizing formulas, but about understanding the underlying principles and applying them to solve problems. As you continue your NEAT preparation, don't be afraid to ask questions, seek help when needed, and most importantly, stay curious. Physical chemistry might seem challenging at first, but with dedication and a thirst for knowledge, you'll be well on your way to acing the NEAT exam and unlocking a world of opportunities in science and medicine. Remember, the journey of 1,000 miles begins with a single step, and you've already taken that step by embarking on this learning adventure. Now go out there and conquer the world of physical chemistry.